Ladies and gentlemen, very good morning, good afternoon, good evening, depending upon from where you are, I think, connected. On behalf of Bharat 6G Alliance, which is an industry, academia, startups alliance in India, it's my privilege. I am Rajesh Pathak, Director General, and honor to welcome you all to today's 6G Leadership Tech Talk. This we have started since last year, and we invite leaders in a specific technologies to share his thought process on some topic related to 6G. Today we have 6G goal of ubiquitous connectivity. One of the goal which is very important for India because our Bharat 6G vision document of the government, it says that it has to be affordable, sustainable, and ubiquitous. So it's one of the important goals. So let me uh, invite today Dr. Houman, a global thought leader in wireless communications and a distinguished contributor to MathWorks, with more than 2 decades of pioneering work in signal processing, mobile systems, and simulation tools, and as the author of Understanding LTE with MATLABs. Dr. Houman brings not only technical depth but also a rare clarity in computing, communicating complex ideas and elegance. In today's session, he will guide us through the fascinating world of non terrestrial networks, exploring how satellites and other medias can bridge the digital divide, and expand the very boundaries of what connectivity can mean. From link budget to beam steering, from hardware implementation to the real world deployment. We are grateful, sir, for sparing your time and expertise with us today. With this, I think I will invite you, and I request others all to please switch off their videos and mute mobiles. With this, sir, I just invite you for your talk. You can do the 45 minutes presentations, and subsequently we will have certain question and answer at the end of your talk, and that we will get from the public chat, or even I will myself or Asthas, he will be just helping at a time. Thank you, and over to you, and all the best.
Thank you very much, Rajesh. And I want to thank all the audience to this webinar. As Rajesh mentioned, it's my pleasure to be here at this Bharat 6G Alliance Tech Talk presentation. Title of 6G Goal of Ubiquitous Connectivity, Connecting the Unconnected Using Satellite Communication. So if you look at the next slide, you'll see that I put it into context, what we know about 6G and its goals. So 6G is the next generation of mobile wireless communication system. As it evolves, we see more and more that's built upon the strength of 5G. So these mobile communication systems that are introduced almost every 10 years complement each other, evolve each other. And as Rajas mentioned, it's obvious that the notion of ubiquitous and sustainable connectivity, those are the areas where the authors and the designers of these systems are emphasizing. The time for every standardization is about 10 years from the last one. Last time we had 5G published, that was in 2018. And based on that, we believe that sometime in 2028, 29, 30, we might have the actual standardization in place. But the research and development in this area is firmly underway, and various industry and academic consortiums, including Bharat 6G Alliance and other colleagues are proposing technologies and advancing this field. If you don't mind, for the next slide. So what we know is that the ITU, the International Telecommunication Union, which sets the essentially goals, and then the third generation partnership product 3GPP decides on technologies to achieve those goals. The ITU has done a lot of work in that area. For every generation, there is an IMT document, and IMT 2030 is a document that ITU publishes for 6G. It was IMT 2020 for 5G, IMT 2010 for 4G. And as you can see, we identify three areas that is the continuation of the 5G mission. They just changed the name. The immersive communication stands for enhanced mobile broadband. Massive communication stands for massive machine type communication. And hyper reliable low latency, replacing the ultra version. So these three, broadband and massive and time sensitive communication, are the goals that are still in place for 6G as well as it was for 5G. But those new things that you see on the screen, the first one is our topic today, ubiquitous connectivity. And then the two other one is the adjacency of communication and AI, communication and sensing. So these are the areas where we see some serious activity and research going on. Go to next slide, please. You notice that the ubiquitous connectivity needs a little definition, and essentially we're talking about high-speed internet access for everybody in every corner of the world. Doesn't matter if you're in a rural area, which means that the mobile communication towers are sparse and far away, and so on. Suburban area, urban area, remote mountainous area on the high sea. No matter where you are, the goal of ubiquitous connectivity is we're going to give you a basic baseline of connectivity in terms of how many megasamples per second you can achieve or arrive at. So if you want everywhere in the world to have that connectivity, this notion of satellites, or sometimes they call it base station in the sky, right, plays a role. Because if you have a high-performing satellite with nice received power in all of those areas, then your devices can directly or indirectly connect to satellite, and that's how you connect to the internet. That's the notion of ubiquitous connectivity in that area. So if you go to the next slide, my friend. So what is this coming from? The trends and drivers for the expansion of satellite communication has been long-term coming. The origins of satellite industry was in the space exploration in the 1960s and so on, and aero and defense applications. So what's happening now is that technology is finding its way to civilian and to commercial applications. And it seemed for a while that there was a conflict between the wireless, mobile, terrestrial service providers and the desire to enable satellite communication, but those discussion has been happening. The hesitancy has gone away, and now the whole community is embracing expanding your area of wireless communication to include non-terrestrial or above terrestrial support, which means satellites as base station in the sky. This is a hot area, lots of investment, many companies, both in the aerospace and defense side and communication, electronics, semiconductors, are investing in this. I don't have to tell you, this is all in the news. And we think that trend and in terms of availability of finances and investment, is going to make this area very successful. So if you go to next slide. So what are the technologies that are new and fresh and enabling all of this? So in terms of the platforms, geostationary satellites have been used for a long time to relay communication messages. If you're watching some kind of a World Cup of soccer or Olympics, you're using geosatellites to beam it to you from all over where the stuff is taking place. But the notion of MEO and LEO satellites, the medium Earth orbit or low Earth orbit, has been the technology that is enabling a lot of stuff. And in the area of emergency support, when the infrastructure is compromised by natural disasters or other stuff, this notion of high amplitude platform station HAPS, I've had many conversations that they're going to put that into the 6G context for emergency services, and that is also another enabling technology. So what are the technical drivers? The small satellites, so that makes the creation of a large constellation of low orbit satellite easier. Despite being small, they are high performance and high power, and they enable 5G and Internet of Things connectivity. MIMO and beamforming is very important, because if you want to achieve, even at these LEO more reasonable distances, some nice power at the ground, you need lots of beamforming associated with that, and the corresponding modulation and coding. So there is lots of bread and butter communication research going on in order to support the LEO platforms and MEO platforms and HAPS that are going to be helping with the 6G. Now, if you go to the next slide, this what we call non-terrestrial network on the right-hand side, based on satellite communication, they are not the only ones. These are all different kind of networks that interconnect to each other. So the typical cellular network, 5G, 4G LTE, and so on, they are dubbed as wide area networks, and there is a plan to connectivity and handoff and coordination between the transmissions through satellite, through cellular infrastructure, and even offloading it to Wi-Fi, local area network, when you have Wi-Fi networks, ad hoc networks like that available, and even personal area networks, Bluetooth, and so on. So the interconnection of these things is one of the challenges of 6G, as we will learn about it. If you go to the next slide. So let's just have a nice definition of non-terrestrial network. So use of satellites and commercial drones as a base station in the sky. As I mentioned, you put satellites in the orbit, mostly LEO satellites. They're close enough to be able to have a high receive power on the ground in the transmissions, and use them to connect devices anywhere on the globe. And it complements and partially replaces part of existing terrestrial network, so, and especially adds those places where there is no investment in base stations. So you achieve coverage and service everywhere. You bridge the digital divide by providing this connectivity, and you realize critical applications in natural disasters that I told you HAPS are very useful for that. We move on to the next slide. So I'm just drawing a picture for you here in terms of how these things will work. So you see, on the top, we are looking at the geo satellites, we are geostationary, MEO and LEO satellites. And if you are non-stationary, your satellites, especially in the LEO and MEO ranges and elevations, they will actually rise from the horizon where you are. They are in your visible range, and your device can connect to them, and they will set in the horizon. So you have a certain amount of time to access to them. And that's the main challenge of satellite communication for ubiquitous connectivity, NTN, is that you can't rely on one satellite. You have to rely on a constellation of satellites. Each of these satellites will rise and will actually come out of a connection in your visual field, and you have a certain time to connect to them. And after you connect to them and they're gone, you have to connect to next one, and so on. Not only those are the players, the satellites, but you see that it is important to have inter-satellite link, or ISL, that are very fast. Lots of our customers are talking about optical communication as a way of inter-satellite links. Because as you know, the traffic is aggregated by multiple users at the satellite. And this aggregated traffic could have large bandwidth and large usage. So you have to go to the next level, go maybe beyond RF, and maybe use visible light for communication between them. But you see, as you are using these LEO and MEO satellites in the context of non-terrestrial network, they connect to flying airplane, they connect to ships, they connect to NTN backhauls, terrestrial network, base stations, ground stations, the Wi-Fi hubs of buildings, and so on, and service directly to UE. I was in a conference the other day called Mobile World Congress, and many companies were showing their plan very soon in the near future to connect the LEO satellites directly to your handheld devices. So this is coming even before 6G, but that's the notion of non-terrestrial network we're talking about. So if you go to next slide, please. The motivation is clear. You want a global service coverage, and even the large isolated areas where there is no investment, there is no economics of scale to invest in that area, NTN can provide help. And if you have a very nice big pipe of inter-satellite links that can aggregate the traffic, then you can essentially aggregate the traffic from the ground using inter-satellite links, can increase the coverage. And for example, many papers that they work with us, they say that, for example, we want more than 99% of the population of the world have at least 1 megabits per second, which is the lowest bar for broadband access, and at least 100% of the world to be covered. Maybe that 1% doesn't have the 1 megabit per second, but they have something, and they can actually connect to internet. So that's the idea of motivation for 6G NTN. Don't mind going to the next slide. So this is good. NTN is good. It's going to provide you with lots of options beyond cellular connectivity and Wi-Fi and Bluetooth and so on. Are there technical challenges associated with them? And you can see here some of the ones that our customers are talking to us about. One challenge is and this is a challenge that in all 6G areas are common between them. 6G will be very responsive system, meaning that nothing is static. Everything is dynamic. As the situation changes, you're going to sense it and you're going to react to it. So one of the things, beamforming and array design and deploying of arrays on the LEO satellites and so on and so forth, has to be very dynamic, and you have to know exactly where your target UE or your target base station is for your satellite connectivity. So your main lobe of your beamforming is in that direction. So a lot of sensing and adjusting and beamforming is going on, and that provides a big challenge. Lots of people are working on that. The notion of inter-satellite links, ISL, I told you about, is very important to have fast ISL links. And usually customers are asking us about optical channel models because they want to go beyond RF links, use optical links. And that combination of optical communication on one side for the inter-satellite link and RF communication on the other side for the ground station and base station and UE links, that is something that requires lots of work and coordination. And then routing, scheduling, networking. As I told you, by definition, this LEO constellation of satellites, they need handoff of a link from, if I use my cell phone to connect to a satellite, I have access to satellite number one for about 2-3 minutes. Then as the satellite number one sits in the horizon, I have to reschedule my phone to connect to another satellite that's visible to me, and all these handoff and so on have to be coordinated. So these are some of the challenges you see with non-terrestrial networks. Now, if you look at the next slide, for example, this is Australia, and we are looking at the signal strength received power from a bunch of these constellations across the country of Australia. And you see, you need to be able to dynamically assess. This is at 1800 hour and 180200 hour. You see, because these LEO satellites move fast, the received power moves fast. And then you have to coordinate the availability and the handoff according to what you measure at the ground at signal strength. So this is an example of scheduling the networking research needed for 6G NTN. If you go to the next slide. Again, routing challenges for ISLs. So you have various routing challenges and mechanisms for the inter-satellite communication. It's a rich area of research, and lots of topologies are being examined in that area. All of this have in common is that you have to know the exact location of each of these satellites in the constellation to be able to their location, their velocity, their acceleration, all the Newtonian mechanics characteristics, so you can address these routing challenges. So that's something that is very useful to have. Next slide, if you don't mind. So what does the 3GPP has done in terms of enhancing the non-terrestrial network? 3GPP is a standard body, as I mentioned, that has been responsible for 3G, 4G LTE, 5G, and chances are for 6G. The 5G documents are represented in technical report 38 dot something, and in release 16, I think, or 17, the 3GPP published the narrow band and later on wideband NTN channel models. Channel models are just the beginning. If you don't have a channel model, then you cannot estimate the link performance. So these channel models have been published, and based on that, if you go to the next slide, based on the published channel models, you have to go and do this analysis on the throughput. Link level simulation is very important for NTN. So I mentioned to you challenges of routing and scheduling and ISL and so on. These are at the network layer. How about at the physical layer? What do you have to do to make sure that your non-terrestrial network works? So if you're talking about communicating between a satellite communication, LEO satellites, and your your UE, your handheld device or base station, you need to have a link level simulation based on physical layer characteristics. And as a function of SNR or as INR and so on, have this notion of throughputs or bit error rates or block error rates or packet error rates, all of these metrics. So in order to do that, you need to have the end-to-end channel models. The one that published by 3GPP are used. So what we have done in our tools in MATLAB, we have a complete throughput analysis of 5GPS. PDSCH stands for physical downlink shared channel. So if you are using 5G or 6G for your downlink or uplink, then you're using those channels. So we have done that together, and we can see that depending on different SNR profile, you get different throughput, and you can see. So if you go to next slide, if you don't mind. So this is the story of what we have, and our customers ask us for it. We have put together in our 5G toolbox, and we are sharing it. So if you're looking for 5G NR, new radio, non-terrestrial network link level simulation, you have to measure the link performance. And the link performance is at the mercy of your transmitter operations, your channel model and impairments, and your receiver operations. Let's say your transmitter operations are 5G NR. So you see on the top of this block diagram, I am putting all the 5G transmitter operations as per 38.101 standard. So you see, you have downlink shared channel, physical downlink shared channel, pre-coding for beamforming, cyclic prefix OFDM. These are the building blocks with all the details for building a 5G waveform that's going to be used for transmitting bits and data from satellite to your mobile, right? That's the transmitter operations. Everything you see on yellow or kind of a light orange are channel modeling. Now, channel modeling has multiple characteristics. Some of them is device modeling or impairments. So you have power amplifier. These NTN networks are very power sensitive because of the distances, large distances between the satellites and your base station or satellites or your handheld devices. You need large power amplifiers. Not only there are large power amplifiers are needed, these satellites move very fast. As I told you, they rise and they set in the horizon within 2-3 minutes for every satellites, for you to connect to them, the LEO satellites. So if a satellite is moving fast and that's your base station, then you have Doppler effects, serious Doppler effects, plus minus, 80 kilohertz Doppler effects. And because the subcarrier spacing usually is 15, 30, 60 kilohertz, so these Doppler effects seriously impede your inter-carrier interference, inter-symbol interference. So you have to compensate for them. So you see, the challenges at the link level simulation are rising up to the bubble. You need the NTN channel model, flat fading and frequency fading as provided by those ITU and 3GP documents. You need a good power amplifier. You need Doppler compensation before transmission or after transmission. Before transmission is based on nominal speeds of your satellite, so you can predict. But after transmission takes all the other stuff into account. And then you see on the bottom the typical 5G receiver operations. First, you have to time synchronize, find the beginning of the 5G frame. You have to do the cyclic prefix OFDM demodulation. Based on that, you have a time frequency grid. You have to find estimate the channel when you find the channel estimate, you do the inverse operation, you find the equalizer, and after equalizing, you do the estimation of the received symbols, and after coding, received bits. So this is a full link level simulation link. This model is available with our 5G toolbox and satellite communication toolbox. And this shows you, highlights all the elements that have to come into play: transmitter operation, receiver operation, power amplifier, digital power amplifier pre-distortion, Doppler compensation, and NTN channel modeling. All of that has to happen for you to know how much bits per second can I expect for my satellite communication link. If you don't mind going to the next slide. So, to summarize, we have looking at the importance of non-terrestrial network as part of the 5G. They're emerging as part of 5G, and they are supposed to be a major contributing factor to ubiquitous connectivity in 6G. As I mentioned, our satellite communication toolbox and 5G NTN channel models in the 5G toolbox, they provide you lots of availability of modeling and simulation to look at NTN and see if what we expect of it is reasonable and realizable or not. So if you go to next slide, if you don't mind. Okay, so NTN, or non-terrestrial network, as a vehicle to provide ubiquitous connectivity for 5G and especially 6G. But NTN relies on the typical and common challenges of satellite communication design. So I provide for you here a list of categories of challenges that every satellite communication engineer has to deal with in order to design a system that is capable of contributing to NTN. So what are the typical challenges? So my friend would hint at telling me, ask yourself 3 questions. Can you see me? Can you hear me? And can you talk to me? So when you ask the question, can you see me? You're looking at trajectory and orbit modeling. Is the satellite you're connecting to is actually in your visible field? Can we see it, right? And considerations like what kind of satellite are we talking about? GEO, MEO, LEO? What is the orbit propagation mechanism that you're talking about? Do we have visibility and link analysis? Can we coverage the whole Earth? Can we see the whole constellation? And at any moment, the distances between every pair of satellites, and trajectory and line of sight. The second question is, can you hear me? And that's link budget. So as I mentioned, satellite communication. The LEO satellites are envisioned to be 500 to 1,000 or 1,500 kilometers, not meters, kilometers above the Earth. Remember, when you are flying from, let's say, India to US, the airplane runs at 10,000 meters. That's 10 kilometers. So airplane runs at 10 kilometers above the clouds. Satellite, LEO satellites, is 500 kilometers. So if you have 500 kilometers, you can expect a delay, of course, which is equal to speed of light divided by the distance, 500. And then you also expect power to be degraded because, every RF and even optical system, the strength of signal is proportional to the inverse of the distance. So link budget is the study of how much my link between my satellite and my base station, or my satellite and my handheld device, how much power budget do I have? How much my transmitter output power have to be that doesn't violate the laws of my country, but also provide enough receive power? Do I have link availability? How about if there are sensitivity analysis, propagation, and so on? And metrics like as carrier to noise ratio, EBNO, link margin are usually discussed within the link budget. And then, can you talk to me? So let's say you have enough power and I can see you, right? And I can beamform toward you. But I have to get some bits. I have to modulate them. I have to transmit them. That's called modulation and encoding, waveform generation, channel models, receiver algorithms. All of that has to come into play. So our satellite communication toolbox, which was released in 2022, is providing all the answers for these kind of challenges. If you go to the next slide, if you don't mind. For example, let's say orbit modeling and simulation. About 600 years ago, Kepler provided the first rules of orbit propagation in his seminal work. So we provide that in our solution. But you also have custom designed trajectories. You can design the trajectory of satellite in any orbit. And there is a standard for it, two-line elements or TLE file. TLE file is common between anybody who is doing satellite communication. So it's a kind of an ASCII file, is a text file that has two lines and describes for you the location and the propagation of the positioning of every satellite. So if you have a TLE file, you give it to our tools and we can actually visualize every satellite around the orbit. So that is what you see on the screen is a snapshot of satellite communication toolbox visualizing a two-line element, two satellites, green and red, around the Earth. So if you go to the next slide, all right, that's one thing. How about beamforming and transmitter and receivers? So not only the satellites are physically steerable, meaning that somebody can give a command and this satellite can physically turn different pitch and angles, but also digitally steerable antenna arrays. So satellites rely on antenna arrays of different geometries, and digitally you can change the beamforming angles. And if you do that, you point antennas to a fixed point on Earth, either UE or base station or ground station, and you can optimize the antenna design for your transmitter and receiver. If you go to the next slide. Path trajectory and instantaneous position and velocity. So this part of satellite communication is all classical mechanics. The speeds are not close to speed of light, so we are not into the realm of relativity too much. We're in the classical mechanics. So you need a 2D and 3D plots. You have to have a ground tracking every satellite, field of view. Looking up in the sky, you see on the left-hand side how many satellites, LEO satellites, are visible to you at any moment. That's called sky plot. So you need to have that path trajectory very easy for you to see so you can plan your transmission based on different atmospheric conditions, based on different density of your users on the ground. Next slide, please. Now, how about time varying access analysis? So as the satellite is moving, the contour of visibility, like the area on the Earth which can see that, will change. And you need to worry about steering constraints, ground station minimum elevation angle, because Earth is round and there's an elevation that below which we are in the shadow of the Earth. So you have to know that. And terrain and Earth curvature affect that minimum angle. If there's mountainous area or if it's a wooded area, you have less visibility than flat Sahara Desert. So these are important, and these tools that we have help you to know at any moment how much access do I have. Go to the next slide. So how about that? So you're communicating, let's say, from India all the way to Australia, and you're using LEO satellites. So maybe one LEO satellite is not going to be placed at any moment the right location with the right angle and right visibility and so on between India and Australia, or India and US, or Europe and Africa, whatever. So what do? You rely on multi-hop communication. Multi-hop means a signal is transmitted from ground station or your base station or your handheld device to the first visible satellite. Then the satellite finds the next satellite in a chain of satellites that it is visible to, sends the information there, the other satellites. And imagine our tools enable you for a constellation of satellites and for a particular link, enable you to tell you exactly the beginning and end of start time and end time and the duration and which satellite is in use to connect any 2 points on the ground. That's the story. So link closure time for each of them and when the link is actually being closed. That's called link analysis, available for our tools easily for you for satellite communication. If you go to the next slide. How about link budget? Link budget essentially is the application of conservation of energy, meaning that you have a base station in the left-hand side, you have a ground station in the right-hand side, and I just give you a bunch of well-known losses and gains associated with this communication. Interference loss, antenna mispointing if the antenna is not beamformed properly, free space path loss, 1 over r squared, where r is distances. So you add all these gains and losses and you compute metrics such as carrier to noise ratio, EB over N naught, link margin, and you want that to be dynamic. And our tools allow you, as the satellite is moving, as the ground station is getting different satellites and connecting with different satellites, we can update this link budget as a function of time. And that way you know realistically what kind of a link budget and link margin you have. So based on link margin and how much received power, you can estimate how much megabits per second you can pipe through that link. Next slide, please. How about propagation loss models? What is the sources for propagation loss models? MATLAB has a lot of channel models and propagation loss models, but we rely in this case on the published ITU P.618. It's the one used ever since the beginning of space exploration, and we are using that. It allows for cross polarization discrimination, sky noise temperature, rain loss models, so you can actually depending on cloud and rain coverage, you can actually update your link budget based on these channel models. And no matter where you are in the world, you can have regions of link availability. So we rely in our tools to help you with NTN and satellite communication on the published ITU channel model and propagation loss models. Okay, how about those waveforms? Okay, now I can see you, I can hear you, you have enough link margin. What are the waveforms people talk about? Beside the 5G, which is the foundation, or 6G, which is the foundation of NTN, seems, or LTE or 5G cellular waveforms, people have used these kind of waveforms in satellite communication, DVB-S2, S2X, RCS, CCSDS, GPS, and GNSS for satellite navigation. So our tools in MATLAB for satellite communication NTN has all flavors and all parameters related to these waveforms. Next slide, if you don't mind. And so having a waveform is one thing. Waveform is transmitter operation. It's all in the standard body, and we have the functions for you. How about if you want to do end-to-end, let's say DBS2X or DBS2 or RCS, link level simulation. You have the transmitter operation and the modulation schemes. You have the channel models that I mentioned to you. How about receiver operation? You see here, this is the DVB-S2X bit recovery receiver building blocks and functions in MATLAB for you to use. So for every one of those compensations, let's say for Doppler compensation or for demodulation, decoding, descrambling, all of that, there is a function in MATLAB, and you can use it with satellite communication. And you can go from this received non-equalized signal on the left-hand side to your equalized and easily decodable signal on the right-hand side. If you go to next slide. As I mentioned, it's an active area of research, high throughput inter-satellite links. So you have optical links as well as some people want RF links for inter-satellite communication. And the channel model is different and the characteristics are different. And we have introduced many optical communication link channel models in the latest version of our satellite communication to help you with the design of the inter-satellite links. Go to the next slide, please. High density satellite constellation. Right now, there are few companies providing LEO satellite constellations, and chances are in the next years, the number of satellites in the sky is going to go much higher. So you need high density satellite constellation. You see here, we have about 1,000 satellites in the orbit, LEO satellites, and that's the same tool we're using, Satellite Communication Toolbox. And any pair of those satellites, their position, their velocity, their distances, and how we can communicate between them is monitored by our tools. So you can actually, for high density satellite communication, provide a lot of good performance expectations. If you go to the next slide. So non-terrestrial network is one of the 6G technologies. I cannot, at the end of this talk, I want to mention the two other ones that are important: the application of AI, artificial intelligence, and machine learning, as well as the notion of integrated sensing and communication. Let's go to the next slide. There are others as well, but we're going to focus on that. So AI and ML, the machine learning, has been applied a lot in our tools to show you how you can use them for future wireless communication design. And the typical application, network management optimization. Some of our customers, I just met them in a conference, they use our satellite communication for the LEO satellites and then use AI to optimize the handoff. So this kind of application of AI for network optimization, end-to-end system optimization, RF, and air interface is used a lot. And we have lots of tools and also knowledge base to show you how you can design and train and infer from AI models into your wireless communication system. Go to the next slide. Integrated sensing and communication is, or ISAC, is a very hot topic because the notion is that in the future, digital twin plays a big role in wireless communication. There's digital twin of base station, digital twin of satellite, digital twin of that. And essentially, these digital twins are AI agents that update themselves based on the sensing information, the communication of the sensing, and what they do in terms of action to keep up with the dynamic system. 6G is going to be very dynamic. And the notion of using RF signals to learn about the physical environment, communicate that to the other side. So based on that, they can do the proper beamforming or proper steering and so on is very important. And we have multiple applications on that. If Go to the next slide. And all of this stuff, satellite communication, integrated sensing and communication, the application of AI, they are computationally intensive. And we have done a lot in our tools to make our simulations, modeling and simulation for you, faster. And so beside the local CPUs and CPU clusters, cloud computing, GPU, FPGAs, there are various tools in MATLAB to help you take the same algorithm, just run it faster. And I have multiple presentations on that if you want to talk to us about doing that. With that, I'm going to go to my summary slide. Ubiquitous connectivity is among the 6G goals for next generation wireless systems. The non-terrestrial networks and satellite communication play a big role in providing ubiquitous connectivity. And modeling and simulation, what we provide in MathWorks and other tools, can help engineers mitigate various challenges of system design by predicting the performance before they actually build the prototype. And other 6G technologies, including satellite communication, can pave the way for universal connectivity. With that, I want to thank you and hand off to Rajesh and my friends to see if we have any questions that I can answer at the end of this talk. Thank you.
Thank you. A really very insightful presentation. In fact, for the first time, even I'm going through such presentations on NTN. So, sir, there are certain questions. I can see the two questions. If you just say these are the various questions we have received, but perhaps more important will be first you can see the questions in the chat box, public chat. So there is at the left side you will see. So Mr. Ansu Kumar, he is asking how coexistence of NTN and NTN provides ubiquitous connections, at what scenario which link is better, and how latency is minimized so that it meets 6G KPI consider signal is coming from NTN. So that is his. And again, one questions I can see from Mr. Pankaj Kulkarni at the last. So he has asked certain questions, sir, and certain questions we have received through registrations we have mentioned here. So if those are not specifically covered, you may just
I
try
can
to cover
start with
them.
a question from Mr. Anshu Kumar, right? I can do that if you like, right?
Sure, sure,
Or
sir.
yeah. So the coexistence of NTN and TN, non-terrestrial and terrestrial networks, how does it provide ubiquitous connection? Is because of the handoff at any moment. So if your future, and I was told in a conference called Mobile World Congress that in 2026, in some part of this world, your cell phones can actually talk to LEO satellites directly. No extra antenna, nothing. This iPhone to the satellite. So if that becomes reality, then essentially you have added another base station to the terrestrial base stations. And when you are outside the range of the terrestrial base stations, maybe when you're in a car or ocean or whatever, and your cell phone can connect to the nearest LEO satellites, that's how coexistence of these two can provide ubiquitous, because it provides another handoff, another offload to a different device. At what scenario, which link is better? That depends on the location. If you're near a base station on the ground, chances are you stay with terrestrial network. But if you're far away from it and you're looking for the best available link, then that is the notion of non-terrestrial. How latency is to minimize so that meet KPI. So latency minimization is a good goal, but there is limits to it, right? So if your LEO satellite is at 500 kilometer divided by speed of light, you have some kind of 10 millisecond or 20 millisecond basic latency. So you have to, when you switch from a terrestrial to non-terrestrial stuff, you have to expect a little bit of latency. and that is something that the quality of service will give you. So that is something that as these systems come online, they may have a little bit of a latency lack of expectation, and then that could affect the impression we have of these things. Okay. Any other question you want to answer? I think you mentioned the question from Ankaj, right? Your view on standardization evolution for NTN. Any trends that you could observe? How TN and NTN integration enabled? Any views on the search aspect? How HREQ rel changes unique to NTN will overcome mitigate? So NTN had a big 3GPP update in release 16 and 17. Lately, I haven't seen much, but I think it's coming when the large constellation of LEO satellites become much more realistic to build. And on the research aspect, a lot of people are working on various aspects of NTN that are very exciting to us. So one aspect is the networking, because as you know, this handoff between various satellites in the view and the use of AI for that. So I see a lot of AI modeling and simulation applied to the handoff based on receive power. So you run a simulation based on the location of this LEO satellite constellation. At any moment, you measure the receive power at the base station or your UE of your interest, and based on that, you decide which one to connect to. And there's so many things you can play with that. The HARQ is affected because of the losses and the notion of if you miss a frame or if you miss a packet, what do you do? And that is also exacerbated by the availability of large delay or latency. So that definitely goes hand in hand. Any other question of interest? Could you please share your thoughts on the channel model between satellite and HAPS network? So again, the question is about the channel model between satellite and HAPS network. Between satellite, which is around 500, 1,000 kilometer, and the HAPS network, which is maybe just a little below airplane, cruising altitude and so on and so forth. Essentially, channel modeling relies on the cloud, O2 absorption, CO2 absorption, and rain profile. So the channel modeling has to be dynamic, and the channel modeling has to take into account at those frequencies what is the effect of rain and clouds on the connectivity between the satellites and the HAPS and perhaps the base station or even other kind of stuff like that. So that aspect, the O2 absorption for higher frequencies and CO2, the rain and the cloud is the most important aspects, and they become part of the large-scale fading questions. And challenges regarding ASICs and custom SoCs in NTN communication. Why only FPGAs are used? Well, I don't think FPGA is going to be always the only platform. FPGAs are very good when the system is not fully standardized yet, which is the case for many of these things. And you want a flexibility of tuning the parameters in real time. FPGA allows you to actually tune your parameters in real time. That's why FPGA is more helpful. But when the standardization is done and everything is all settled, ASIC could be faster and better way to do that. And custom SoCs, because chances are the spirit of ORAN is in play here. Many of the RU stuff happens in FPGA ASIC. Many of the DU stuff happens in GPU and CPUs. So if you have a SoC and you can have communication either between those stuff in satellite, actually, that would be great. So all I'm saying is there is no reason to believe every signal processing on a satellite communication NTN link is done on FPGA only or ASIC only. There's going to be place for GPU and CPU, and people are exploring all of that. What is the waveform expected for NTN operation, and how is it different in handling sessions compared to just 5G network? So, as far as I hear from my customers, the NTN in the 5G or in the 5G era, like now, if NTN becomes a reality in some parts of the world, it's based on LTE and 5G waveforms. It's amazing how many customers we have who are in NTN business. They're asking us for LTE toolbox because the beginning of the NTN coverage starts with voice communication. Maybe the video and images and so on comes later. And because the LTE has established, and I guess cheaper in terms of voice communication, and much more, how do you say, much more forgiving to delay profile, we see a lot of LTE waveform being used by our customers in NTN, and also 5G lower bandwidth waveforms, not as high as a 400 megahertz, but let's say 1 megahertz, 5 megahertz bandwidth. So that's what we see, LTE and 5G low bandwidth waveforms for NTN. Question about what's a trade-off between Earth fixed beams and Earth moving beams, what are preferable to use? So it depends, right? So fixed beams essentially say that the mechanical positioning of the satellite to the ground or satellite to UE is good enough for my beam forming, whereas the non-fixed beam, the moving beams, assumes that the UE or base station or whatever is moving around your car, your vehicle, your ship, and then you need to update your beamforming. So, and for the 6G, everything will be moving. So everything that you assume to be static in 6G, that's kind of a bad assumption. And another question here: what adaptations and new protocols are being developed at physical MAC and network layer to secure communication layer over high latency and additionally lossy satellite link in 6G, particularly in the context of 6G? So all of that stuff is being done together. Unfortunately, the days that you can do physical layer design, forget about it, MAC layer on top and network layer on top is over. And one of the areas is cross-layer beamforming. My customers are talking to me about that, right? So you get the information from the physical layer MAC, then you do beamforming at the application layer, come back, and so on. So lots of stuff is happening here, and the main, as you can see here, you mentioned the main challenges. The main challenge is power, and the main challenge is delay. So can you squeeze maximum with given delay at this power? That's the challenge and adaptation for the protocols. And there is no answer except modeling and simulation. You have to model and simulation and use clever techniques to squeeze maximum out of the available, link margin with your delay that you are saddled with. Right now we are beyond 6:37 here. Rajesh, you tell me how much more do I answer questions, or I would love to answer all of them, but if you have any time limit, let me know. Otherwise, I keep going.
Uh, I think we are honored to have you, because since you have been the author also, so there is a lot of questions, and since they are getting the answers,
I just keep
even I
going,
am.
right? I
You
keep
keep
going.
going, and I'm surprised there are 79 online and so much on YouTube. So I don't have
Well,
any answer.
hopefully,
I think we can just
hopefully
wait. Yeah.
we will work with you guys at collecting the questions that I couldn't answer. I can work with Prashant and my friends from MathWorks India to respond back. At least in written form, if I didn't answer questions properly, and we can
Sure,
get the
sir.
conversation going. I don't want to leave anybody unanswered, but there's just too many. God bless. Last time I was in India, I was in the front of 1,600 audience. I know that sometimes the eager engineers and lots of questions, lots of people. So if I cannot do it in the allotted time, I promise to do it offline. Don't worry about it. And
So, sir, please
uh,
continue. So much I think you feel they are
yes, yes.
relevant. If they are relevant,
Yeah,
then please answer.
I'm looking at the top
Let
to
us
bottom of this
do
question.
next. Yeah, let us do next 10 minutes. Yeah,
10 minutes.
more 10 minutes.
Okay. What's the life cycle of different generation of LEO NTN satellite? That's a very good question. So they're telling me, well, again, this is something based on so many factors, the physical design and material science and this and that, and government requirements. But they're telling me that the life cycle of LEO NTN satellites are between 10 to 20 years. That's a huge range. So satellite goes up, are in operation for 10, 20 years. And I think what they're trying to do is, instead of just destroying it and having it be space junk, they want to bring it down to the ground and maybe reuse it or something. So that's a very good question. But I keep hearing the word 10 to 20 years for each LEO NTN satellite and their service. There's a plan for their service by bringing them down to the ground and then recycling them. My pleasure. I wrote a book on LTE a long time ago. My publisher asked me to book a book on 6G. So if you guys are interested, let me know. I may do a book on 6G in the next couple of time. And any view on tracking area planning, 5G or 4G, how paging will work? Can we prevent multiple tag updates? Now that's, Yogesh, that's beyond my area of expertise. Sometimes I'll be honest with you. If I don't know too much about the topic, I honestly tell this is an interesting topic, but I am not the person to ask. So it's a very good area, tracking area, but it's not directly applicable to my knowledge base yet. So maybe thanks to you, I will go and read more about it. Can MATLAB provide recommendations for satellite orbit constellations given their constraints like height, etc.? Absolutely. So the best thing about our satellite communication toolbox in MATLAB is you fire up that tool I showed you with that nice pictures and so on, and you just create satellites by its object. Just say satellite, and you get a satellite, and you set parameters, and you put it there in the constellation. And you just specify a TLE file. Each line of the TLE is one satellite, and you make this thing run together. So all I'm saying is by a Monte Carlo simulation, and by actually using other tools we have, like optimization toolbox and so on, you can find out what are the recommendations in terms of the number of satellite in constellation, their elevation, each of them, their orientation, and so on, just by running a Monte Carlo simulation in our satellite communication tool. NB-IoT NTN is another term we often hear, which people are interested. Any reason why it is picking interest? Excellent question. Now listen, NB-IoT was invented as part of the LTE, release 14, before release 15 5G. The the origin of NB-IoT is before 4G and 3G, we had GSM. GSM band is 180 kilohertz, right? 12 subcarriers of 15 kilohertz. And they wanted to not lose the GSM. And they found applications called NB-IoT. NB means narrowband, which is GSM. IoT is the application. Now, IoT, as you know, in the last 10 years, 15 years, IoT, Internet of Things, was a huge deal. Everybody will be connected to internet. Your fridge will talk to internet. Your tooth will talk to internet. I don't know, your monitor will talk to internet. That didn't materialize as much as they wanted to. The only device that is really an IoT device in that definition and is online now is autonomously driving cars. Autonomously driving cars, the electric cars of future, are viewed as an IoT device. And imagine if these devices talk to the infrastructure, talk to satellite even, talk to base stations, talk to each other using an NB-IoT link, using those narrowband stuff. They send each other messages. So that is something that I see lots of our customers are working on. Is IoT means autonomous driving cars, and NB-IoT means using those short GSM bandwidths to communicate quickly between them. Don't hit me, turn left, turn right, that kind of stuff. So that is the interest that I see, my friend, on that front. So I think I done most of these questions, and my pleasure. One gentleman says he has a autographed version of my book. God bless you.
So
I
I
think
think
I came to India last year. I autographed some book. Maybe that's the gentleman I talked to. Yes, I went to Japan once after I published the book, and this nice lady from my company came and asked for my autograph. I felt so special that she was so kind to me. So if I have a 6G book, I come to India for my tour and have many of you see my autograph if you feel like it.
so welcome, sir. And with this, I would like to thank you. I think this is the first time that even till this time, it went up to 90 and then it's 76 online just to hear a author. Because I think you have certain you just shared certain views which otherwise no one is going to share those views. With this, we come to the end, and with me, I have Astha Sharma, she's Assistant Director, Technology, Swapnil Tripathi, and Shah Faisal. So I request Astha for giving the vote of thanks. Uh, Astha, to you.
Sure, sir. Thank you, sir. On behalf of Bharat 6G Alliance and all our esteemed attendees today, it is my distinct honor and pleasure to extend a heartfelt vote of thanks to our distinguished speaker for sharing such a truly insightful and comprehensive presentation on 6G goal of ubiquitous connectivity, that is connecting the unconnected using a satellite communication. It was truly indeed very exciting the way you have navigated such a complex topic. Non-terrestrial network, it is so vital for the 6G era. So it was a very exciting topic, as well as the way you have narrated. You have given so much examples and showed that how the MathWorks is playing contributing in this domain. So and I would also like to thank my organizing team also, Swapnil and Faisal, for organizing this talk, and to Prashant also for helping us in enabling this organization of the talk. Thank you all the attendees for putting up so much of questions, and it was very apart from the talk, we were also excited to learn about more facts through the questions and answers round. So thank you all for your time, and let's see for
And,
what we have in store
and
for the
sir,
next session.
we want your permission to share the presentation to registered participants. Thank you.
Absolutely. It's my pleasure to be here. It was honor to be in this esteemed group of engineers and scientists and a wonderful audience and wonderful questions. Again, I promise to be answering any question I couldn't answer. If you send me the information, I will oblige. And I would love to, hopefully next time I'm in India, pass by and see you in person. I come once every 2-3 years to actual different countries. It was awesome, and you're so kind with your. I don't deserve all of that accolades and kindness, but I really appreciate your kind words.
Sir,
God
we
bless you,
invite
and thank you very
you.
much.
We invite you during India Mobile Congress. There is a 6G symposium on 9th and 10th of October. If you feel, then I think we can invite you, and we can have one talk from you also during our 6G. So I
I
think I will
will
just
coordinate
share.
with you guys later on if that's possible. I would love to do it. If I have if I have some conflicts, I tell you. But if it's possible, definitely I would love to help any way I can. Yes.
Sir,
Thank you.
namaste from India. I think good day.
God bless you, sir. Thank you so much. Thank you. Bye bye for now.